Now, for all of these spans, both for east-west and north-south, both end span and interior span, we have done the calculations and we found out what is the prestressing force per meter and what are the eccentricity that it is possible. Now, this is our initial prestressing force. We are going to assume that 20% are going to be losses. Okay. In post tensioning, because you have a lot of curvature and wobble effect will be there, so a lot of losses will be there. In addition to that, there will also be restraining from columns when you do the prestressing for the slab, because the slabs are attached to the columns, that will prevent this slabs from getting it shortening and getting prestressed. So, accounting for all those things, we are saying that about 20% of them is going to be lost, which is reasonably a good assumption. So, the final prestressing force is working out to be for each cable 137.5 multiplied by 0.8, which works out to be 110 kilonewton. Now, we are talking this for each individual cable, we are calling that as a tendon. Now, we also have multiple systems that are available. You have 4 cable system, you have single cable, you have 2 cable. So, here we are taking a single cable system, right, and for single cable, for each cable that you get 110 kilonewton as an effective prestressing force per kilonewton. Now, what is the determination of the number of tendons? P in the east-west direction is going to be 360 kilonewton per meter divided by the total required force in the east-west was 360 kilonewton per meter, that I am dividing it by 110 for each cable. So, I need 3.27 cables. So, the 3.27 we cannot put, so we can say that it is roughly we need to put at 300 millimeter each cable, right. For the north-south directions, typically shorter directions, we try to put banded cables. Now, let us say that each location will have 10 strands. Let us see how do we get that. So, from that force also again we can find out from the north-south direction what is that force that is required. Then you can find out all of them at that force, which is basically 10 strands for each column. Okay, this is again from the prestressing force you can calculate. We have already done that calculation. So, based on that we can find out how many strands are required. Okay, now that we have found out what is the prestressing cable and their profile, now we have to go for the detailed analysis. Now, the detailed analysis we are going to do a manual calculation, finally we will compare the results with safe results, right. So, we have explained what is an equivalent frame in the previous parts of the module. So, you can look at it, what is that we do? We take a typical substitute frame of the slab and we consider the columns above and columns below to be fixed. In addition to that, I am also going to have, if there are any beams or a part of the slab will act as a beam in torsion. So, this also will be there. So, I am going to convert the column above and column below and this transverse member as an equivalent column, and equivalent column stiffness is KT into summation of your stiffness of the column divided by KT plus summation of your KC. Now, what is KC? KC is basically 4 into EC into I divided by L minus 2H, which is column stiffness. What is KT? KT is the stiffness of a torsional member which is acting in the transverse direction, right. So, now we have done this from the flexibility analysis point of view. Now, the summation, because we have seen that the rotation at the joint theta B will be lesser compared to theta A and theta C. So, we are going to take an average the stiffness. So, the equivalent column stiffness will be 1 by summation of Kc plus 1 by Kt. So, when you take that, equivalent stiffness Kec will become Kt into summation of Kc divided by Kt plus summation of your Kc. Now, what is Kc? Again column stiffness. What is Kt? It is the torsion stiffness of the transverse member. Now, that also we have seen it in the previous lecture. If it is a L section or a T section, I convert them into number of rectangles in such a way that I get the largest C value, right, and then I sum them up to get my Kt. It is Kt is nothing but the torsional stiffness of the transverse member, and C is your torsional property of the section, similar to your moment of inertia that you have for flexion. For torsion, it is your C, which is function of your dimensions of your member that you are doing the calculation. And when L2 is the length of the slab that is measured transverse to the direction in which the moments are being determined. This is how you get your KT. This is the equation, right. Now, let us look at for each one of them, how do we get it. So, basically what we are going to do for the slab, as we have discussed it in the previous parts, we are going to convert them into a frame. We are going to take typical frames both in the east-west and north-south direction. One interior frame we are going to take and one end frame we are going to take, both in the north-south as well as in the east-west direction, right. So, in the north-south span, now I have to calculate all the stiffness parameters, right. So, we have calculations of the first column stiffness. Column stiffness equation is 4 into EI by L minus 2H. Now, L is the height of the story, right. So, which is 3350 is the height of the story, minus 2 into H, which is 250, and EC into 500 into moment of inertia of the column is 500 by 500 section, it is 500 to the power of 4 by 12. So, you get column stiffness as 7.31 into 10 to the power of 6 EC. Now, torsion stiffness, now you can see that for that particular width of the column, you take the thickness of the slab and assume that there is going to be a beam that is acting in the transverse direction. So, though this is a flat slab, there is no beam that is there, but a part of the slab in the transverse direction will contribute in torsion. So, that is what we are trying to calculate the stiffness. So, I am going to take this as thickness is 250 cube and width of that particular beam I am taking it as 500, and this is the equation that we have shown you. What is the C equation? The torsional property of the section, that works out to be 1783.85 into 10 to the power of 6, right. Now, what is KT? Again you plug in your equation. So, here the span is 8 meters and width of the column is 500. So, you substitute all these things and I get 4.87 into 10 to the power of 6 EC. Now, I got KC and KT. Now, I can calculate the equivalent column. This is your equivalent column stiffness, right. So, 2 into 7.31, which is Kc, divided by 1 plus this, when you add them up, you get 3.65 into 10 to the power of 6 EC. Now, we have done the equivalent column stiffness. Now, I have to calculate the slab stiffness. Slab stiffness is again 4 EI by L and L is slightly modified. So, 4 into ECS into I is for the slab is H cube is 250 cube, and we are considering the entire width in the perpendicular direction, which is nothing but your 8 meters, and the span is 9 meters, so 12 into 9 minus 250. So, you get 4.76 into 10 to the power of 6. And carryover factor is 0.5 for all the joints, because these are all prismatic members, Okay. Now, if you have flat slab or a column capital, slightly these numbers have to be modified as per the tables that we talked about it in the previous lecture. So, now in this case, because it is a flat plate, carryover factor is 0.5 because it is all prismatic. Your distribution factors is now Ks divided by summation of Ks plus Kec. So, you get for end span 0.56 and for interior span it is 0.36, right. So, again we do the same thing for the east-west span now. Kc is the column stiffness again, 4 EI into I is going to be 500 to the power of 4 divided by 12, and your story height is 3350 again times 2 into thickness of the slab, which is basically 2 into 250. So, we work out of 7.31, and torsion stiffness again we are assuming that a portion of the slab will contribute in torsion up to the width of your column width, which is 500, and depth is 250 for the slab. So, 250 cube into B by 3. So, all those things if you substitute, torsion property is 1783.85 into 10 to the power of 6, and KT equation again if you substitute you get 4.23 into 10 to the power of 6. So, you again plug into the equation to get your KEC as 3.28 into 10 to the power of 6 EC, right. Now that you have got the column stiffness, column equivalent stiffness. So, now slab stiffness is again same 4 EI by L into by L. So, L minus C1 by 2. If you substitute that, you get 6.05 into 10 to the power of 6 ECS. Now, we got all the parameters, then I can find the distribution factor as 0.65 and 0.39. This one is for the end span, another one is for the interior span. Okay, let us move on to the step 10, which is basically the determination of the fixed end moments due to pre-stressing, right. So, as you know, estimation of your stiffness properties and then finding out the carryover and distribution factors, and the next important thing is to find out the fixed end moments, right. So, now for a fixed end moment, we can see that this is due to pre-stressing. I am going to have, that is load that it is acting due to pre-stressing is going to be basically fixed end moment can be calculated using this. Basically, we are locking the joint. So, what is the concept of fixed end moment? The joint wants to rotate to certain level, but we are preventing that rotation. That is why you get this fixed end moment. Now, we know that when you have a slab which is subjected to uniformly distributed load, the pre-stressing the fixed end moment is going to be WL square by 12. The signs will change plus or minus depending upon which direction that you are looking at, right. Now, in addition to that, I also have some primary moments due to pre-stressing that it is acting at those end points, right. So, that is already acting. So, we are subtracting this WL square by 12 minus P into E is nothing but your fixed end moment. Now, what is W? W is nothing but P by 12 R that we know, which is basically equal to PL square by 12 R minus small p into E. Now, we can simplify that and find out the fixed end moment as small p into 2 E naught by 3 minus your eccentricity. So, now what is E naught? E naught is nothing but your the overall the drape that what we are talking about. In this case, for example, east west direction in the interior span, E naught is going to be 174, right. So, if you substitute this, the fixed end moment is going to be for an interior span is going to be the pre-stressing force, which is 3410, right, multiplied by 2 E naught by 3, which is 2 into 174 by 3 minus this eccentricity, which is basically your point, this is your 0.022. So, basically your eccentricity at this end point, whatever that eccentricity that you have, basically 94, or other words I should say 94. In this case, it is 94, right. So, if you substitute that, you get your fixed end moment for the interior spans as 75 kilonewton meter, 75 kilonewton meter. Right. Similarly, for the end span, you will find that this drape is 125.38. At this location, the eccentricity is 90.77, and at this location, the eccentricity is 0, right. So, you will find that this is basically you will get this component will become 0. So, it will be P into 2 E naught by 3. So, if you substitute that 2 E naught by 3 will work out to be 0.084 meter. So, when you substitute that, fixed end moment at the left joint in an end span will be 286.4 kilonewton meter, but on the right span right support I am going to get as 3410 into 0.0072. So, if you plug in this value, then you will get your this is the value 0.0072, then you get your 24.55 kilonewton meter. So, similarly, we do that for north to south direction interior span and north to south direction end span, and again the same equation is valid. You get your total drape minus the eccentricity will give me this. So, P is your pre-stressing force, right. So, 1100 is here, and if you substitute this is working out to be basically 2 E naught by 3 minus eccentricity, right. So, similarly, this is also same. So, this 0.007 is nothing but 2 into E naught by 3 minus eccentricity, right. So, this is what it is. So, if you substitute the value, you see that north to south direction, my fixed end moments are 8.47, 8.47. but in the end span I get on the left support 83.6 kilonewton meter, and then on the right support I get 8.47 kilonewton meter. Now, we got all the stiffness parameters, we got the fixed end moments, we got the carryover factors, they are all prismatic. So, the carryover factor is same. So, now we can go back and do the moment distribution method. So, let us look at it. So, that is what we are going to do. So, we are going to take each frame. For example, here is a north to south direction, which is an ideal strip, and we are going to typical way we are going to take interior frame, and in the sign conventions we are going to take clockwise moments are positive and counterclockwise or anti-clockwise moments are taken as negative, and due to symmetry we are going to do moment distribution only for first to two bays only, and carryover factor is 0.5 and n moments due to factored load. Now, there is also load that it is acting. So, we are going to do the moment distribution in two stages. First is due to prestressing, then due to external loads. Okay, this is the fixed end moment coming from applied external load. So, which is 15.75 multiplied by the width, which is 8 meters, span is 9 meters. So, 15.75 times 8 multiplied by 9 square by 12 will give me fixed end moment as 851 kilonewton meter. Now, we are again taking this. So, you can see in the north to south direction I get 83.6 and 8.47 fixed end moment, then the interior span I get 8.4 and 8.4. So, if you take this as A, this as B, this B and this is C. So, we do that, we have previously we calculated your distribution factor as 0.56 and 0.36 and 0.6. Please note that you also have a equivalent column that is there. So, that we are not considering here. So, we are considering only the slab to show for clarity, right. So, carryover factors are 0.5, 0.5 and 0.5, and fixed end moments as you can see 83.6 and 8.47 and 8.47, right. So, you substitute that, then basically we try to balance this and apply this distribution factor 0.56 times negative 83.6, that works out to be 46.82. This joint is already balanced, so I do not need to do anything, but then when I am carrying over some of the moment, it carries over here, right, roughly half of that, and then that becomes 23.4. So, this joint becomes unbalanced, then this has to be applied moment in the opposite direction. So, in proportion to the distribution factor, so 0.36 multiplied by plus 23.41 will work out to be 8.43 in each side. Now, this is okay. Now, I am carrying over further again here, and then in this way I continue the exercise until my carryover moments are become negligible, right. So, finally, when you add all of them, you find your final moments as 39.21, 22.48 and 13.92. These are only due to pre-stress. We have not done the analysis for the external loads, right. So, this is only for the considering the effect of pre-stress, right. Now, again this is for the factored load. So, we do the same thing 850.5. So, you see here negative say 850, 850 and negative 850, and here we try to balance by applying plus 850 and multiplying by the distribution factor. That is how it works out to be 479.44 kilonewton meter. Then half of them get carries over here, and then we try to balance this in proportion to their distribution factors, and then again carryover that happens, right, and then here carryover happens, here carryover happens, right. So, we do that until the carryover moments becomes negligible. Then finally, you add all of them and you find that this is 395, negative 395 and 993 and 906.5, and you will find that this will not be balanced because this joint also have a column above and column below in addition to that. So, that is what we converted into an equivalent column, right. So, that column stiffness also we have to that will take some moment as well. So, when you include those moments, everything will joint will balanced. but here it does not look like it is not balanced, but actually that balanced moment is taken care by the equivalent column. So, now we got the analysis, right. So, let us look at now the final moments due to pre-stress will be 39.21 plus negative 22.48 and then 13.92. Then final moments due to factored load is negative 395. So, this is at A, this is at B and this is at C, right. So, these are the things that we are looking at, and then the resultant moment you add them up and you get these values. Now that we got these moments, now you can apply the free body diagram, find out exactly how the distribution of the moments are, right. So, in this way we have basically what we have done is we have done structural analysis using fundamental concepts for this flat plate by converting the flat plate into a frame in north, south and east, west direction. So, same thing, this is for one particular frame that these are the values. So, now that we got, and this is for the entire width of the frame. Please note that this is for the entire width of the frame. Now, again we do the same process for the east-west direction. As you can see, L2 here is width of the strip is 9 meters, the span is 8 meters, right. And again we are going to use moment distribution method, and due to symmetry here again we are going to show calculations only for the first two bays, and carryover factor everything is prismatic. So, carryover factor is 0.5, and due to factored load again here the width is 9 meters, span is 8 meters. So, it is working out to be 756 kilonewton meter. Again we do the distribution now in two stages. This is only due to pre-stress, okay. Then we do the same thing for external load, then we add them up, right. Again we have done this calculation, fixed end moment for end span at support A, let us say this is B, this is B and this is C. So, fixed end moment at A is 286.4 and fixed end moment at B is you got 24.6, that is what you have here, and on the interior span you get 75 and negative 75, 75. So, we are doing only calculations up to this, the other spans will not affect the results because of the symmetry, right. So, now we try to balance this by applying negative 286 in proportion to the distribution factor. So, 0.65 times negative 286 will work out to be negative 186. Now, this joint has a balance of negative 38 and 38.8, then you get carryover, right. So, you get again you can see the carryover goes here. So, like that we continue the process, right. So, you get this. So, like this we continue until the carryover moments becomes very, very negligible. Then you add all of them to get your final moments. You see here 99.86 at AB, and for BA it is 70.88 and for CD it is 72.53 and so on. So, you get the distribution. These are the moments due to pre-stress only. Again we do the same thing for externally applied load, which is 756 kilonewton meter. Same process, finally you get your final moments at different locations like this. Now, principle of superposition is valid. So, I am going to consider both the effects of pre-stress and the external loads, then you get your moment as this. Final moments are negative 183 points, again this is in joint A, this is B, C, D and so on, right. Okay, sorry, this is AB. Okay, so this is AB, EA, and then BC, and then you have CB, and you have CD. These are the locations. So, these are the moments have been plotted also for easy understanding. So, these are the values.